Let's take a look at what the span of two vectors u and v looks like algebraically. Remember that the span is just the linear combination of all of the vectors in that space. And I have two vectors in this space, 1, 2, and 3, -2. So the span of these is going to be some constant times the vector 1, 2, plus some other constant times the vector 3, -2. And these constants can be anything from the real numbers. So in this case, they're just a particular constant and another particular constant. But because I'm working with generic sort of variable values here, these can be anything. So what I'm about to show you is true for any constants in R2, any scalars. This is going to give me a1 plus 3a2 and 2a1 minus 2a2. So for a vector to be in the span of these two vectors, it has to take this form. Now let's see what happens if we introduce a third vector. And this one I hope is going to be painfully, obviously, a scalar multiple of this one here. And now what I want to do is find the span of the vector 1, 2, and a vector that's a scalar multiple of that vector. So I'm finding the span of u and w, the span rather. And that I can do, I'm going to use different numbers here just because I think that's best practice. You're getting potentially different constants than you did in the previous example, although again, they could be any constant, anything from the real numbers. And that gives me a3 minus a4 and 2a3 minus 2a4. So for a vector to be in the span of these two vectors, it has to take this form. But notice also that I can write the second component of that vector as 2 times a3 minus a4. Right? All I've done, these are real numbers, so all I've done here is factor out the 2. And if I do that, let's say that a3 minus a4, whatever those two numbers happen to be, and remember, they can be anything, we're going to say that's equal to a5, some other constant, some other real number. That means this is a5, and this is 2 times a5. I'm going to move this up just a little bit so I can get some more room here. Now, since a5 is a constant, I can pull that out, right? I'm just unscalar multiplying this vector. And what I have then is that the span of two vectors that are scalar multiples of each other, for a vector to be in the span of these two vectors, it must also be a scalar multiple of the vector 1, 2. Any scalar multiple of the vector 1, 2 will be in the span of the vectors 1, 2 and -1, -2, but all vectors in the span will take this form. So we're only going to get in the span of these two vectors, vectors that are scalar multiples of these two vectors. And that matches what we said in our previous video, that if you have two vectors that are scalar multiples of one another, then the span of those two vectors would only be a line. These are all scalar multiples of those two vectors. Not to scale, but you get the idea. When this happens, when two vectors are scalar multiples of each other and their span, therefore, only includes other scalar multiples of those two vectors, we say that these two vectors are linearly dependent. That is to say that they depend on one another in a linear fashion. The collection of all possible linear combinations of these two vectors produces a line. These two vectors depend on one another in a linear fashion, linearly dependent. Let's take another look at this on the next screen. Okay, the span of u and w, those two collinear vectors, the vectors that were scalar multiples of each other, that span is all the linear combinations of those two vectors. And we noticed that that was just another scalar multiple of the same vector, or a scalar multiple of one of the two vectors. 1, 2 is a scalar multiple of -1, -2, in as much as you can take -1, -2 and scale it by -1 and get +1, +2. So each is a scalar multiple of the other. And the span is made up of additional scalar multiples of that same vector. Now, it turns out that there's quite an interesting phenomenon going on here. And that is that if I wanted this to be the zero vector, all I would have to do would be choose A3 to be 0. But if A3 is 0, remember, I didn't draw this out. I didn't give the details here, but I said on the previous screen, I said A1 minus A2, we'll just call that A3. In fact, I think it was A3 and A4, and I called it A5, but you get the idea. I'm calling the difference of these two real numbers this real number, and I'm factoring that out. This would be 1 times A3, and this would be 2 times A3. Okay, so if A3 is 0, then A1 minus A2 is 0. And what that means is that A1 and A2 are the same number. What's more important is that A1 and A2, although they're the same number, can be any real number. If our goal is to figure out what makes this thing be 0. And what that means is that there are numbers out there, A1 and A2, that make this thing 0. And they don't have to be 0, right? Obviously 0 will work here. If A1 and A2 are both 0, then that will work. But there are other numbers. A1 and A2 can be anything, even 0, and I can turn this thing into 0. That's only going to be true if I can sort of factor these numbers out here, right? That's only going to be true if this if the vectors that I started with are linearly dependent vectors. So this is a test of linear dependence. Are there scalars, A1 and A2 in this case, because I'm only working with two vectors, are there scalars that are not 0 that turn this thing into 0, that turn the span into 0? Another way that I could have checked for this would be to take the coefficient matrix that you see here, which is 1, -1. I'm taking the coefficients of my scalars now, and I'll write those down, 1 and -1, and second row is 2 and -2, and set them equal to a 0 vector, and row reduce this matrix to see what, if any, solutions there are. Let's move this over here so we have a little more room. Okay, the first pivot is already a 1, so I'm going to multiply row 1 by -2 and add it to row 2. -2 times 1 is -2. -2 plus 2 is 0. -2 times -1 is +2. +2 plus -2 is 0. 0 times anything plus 0 is also 0. And what I get here is, let's rewrite this as a system just so we can interpret it. You don't need to do that because this last all 0 row should tell you this, but I'm just going to go ahead and rewrite it anyway so that we can interpret it. What this says is that my variables were A1 and A2 equals 0, and 0 A1 minus 0 A2 equals 0. Well, this last line here just says 0 equals 0. That's what this 0 row in a matrix tells you, 0 equals 0. And that's always true. That's true for any A1 and A2 value, right? It doesn't matter what A1 and A2 are. This statement is always true. So that means that A1 and A2 have to satisfy this equation, but they do that. I'm even gonna cheat a little bit here, and I'm gonna say they do that if they're equal, right? If I solve this equation, that's the same equation as I had here, right? If I solve this equation, I get A1 equals A2. So A1 and A2, well, let's just say that A2 depends on A1. Once I've chosen A1, I have by default also chosen A2. They're dependent on each other. So if when you set up an augmented matrix for your scalars, and your augmented row is 0, your answer column is 0, when you reduce that, if you get an all 0 row, then those two vectors that you started with here are linearly dependent. Consequently, if you don't get an all 0 row, then your two vectors are linearly independent. Okay, let's take a look at an example in R3. Now, in R3, I'm going to need 3 vectors. So let's use vectors u, v, and w. And u is going to be 4, 1, 2. V is 8, 2, negative 1. And w is negative 4, negative 1, 3. Okay, we want to determine whether these 3 vectors are linearly independent or linearly dependent. So I'm going to check to see whether there's a linear combination of A1u plus A2v plus A3w that equals 0. If it does, then they're linearly dependent. If I can make that equal 0, then they are linearly dependent. If I can make that equal 0 with something other than all zeros, right? You can do that. If A1, A2, and A3 are 0, well, then obviously it's going to equal 0. That's the trivial case. If there are other numbers out there that will work, then the 3 vectors are linearly dependent. So let's set up what this matrix is going to look like, and I'm going to do the intermediate step because I think at first it's not at all obvious which matrix you're actually testing for this. So let's set up our matrix. We're going to have A1 times the vector u, which is 4, 1, 2, plus A2 times the vector v, which is 8, 2, negative 1, and then A3 times the vector w, and we want that to equal 0. That's going to be 4 A1 plus 8 A2 minus 4 A3, 1 A1 plus 2 A2 minus 1 A3, and 2 A1 plus, oops, actually minus 1 A2 plus 3 A3. I was very careless up here. I'm going to go back and fix this. This does not equal 0. It equals the 0 vector. So I'll put that in there like that. In fact, I'm going to change this one here just so that you can see where I'm about to get the next step. This is the 0 vector, and because we're in R3, and I know I'm in R3 because all of my vectors have 3 components, right? So the 0 vector has 3 components, and that says that this is equal to, each of these equations is equal to 0. Now, if I turn that into a single augmented matrix, I get this: 4, 8, negative 4, 0, 1, 2, negative 1, 0, 2, negative 1, 3, 0. And I hope that now it's really obvious that although I've written this in terms of the rows, because I'm looking at the equation A1 times 4 plus A2 times 8, and so on, where I've got the values for this coefficient matrix is the columns. The vectors that I have written here as columns, column vectors, right? Column matrices rather, are columns in my matrix. So I could just have gone straight from this information to this matrix to do this test. I would have written this column, and I would write it as a column. There's the same 4, 1, 2. Then this column next, and the third column, W goes here, and then the 0 column is last. Now I'm just going to do this one on my calculator. I'll end up with a 3 by 4 matrix. I'll have a coefficient side and a constant side. I'll just do this on my calculator, and I'll come back when I have a reduced echelon form of this matrix. All right, there, I've done that work. This matrix reduces to this one here, and the key right here is just this 0 row. This says 0 equals 0, because 0 equals 0 no matter what A1, A2, and A3 are. I can find values of A1, A2, and A3 that will make this statement here true, the 0 vector, where A1, A2, and 3 are not all zeros. They're out there, they exist. Just for kind of confirmation, if I take this information and go back over here, my first two lines tell me that A1 plus A3 equals 0. My second line tells me that A2 minus A3 equals 0. And the second of these two tells me that A2 equals A3. And in fact, the first of these two tells me that A1, let me write it this way, negative A1 equals A3. So once I know what A3 is, I also know what A2 is. I forgot my subscript here. Once I know what A3 is, I also know what A1 is. It's the opposite of A1, the opposite of A3. And A2 is just equal to A3. So once I know what A3 is, and I can pick anything I want for A3, then I also know A1 and A2, values of A1 and A2 that will make this statement true. It'll make it equal to the 0 vector. Now sure, A1, A2, and A3 can all be 0, but what this tells me, which is what this tells me, is that it doesn't have to be. They don't all have to be 0. I can find other values that will do this job for me. That's how I know that these three vectors are linearly dependent. I'm going to do one more to show you what it looks like when they're independent. I'm kind of doing this backwards from the way it's presented in your textbook. Your textbook set says that a set S that's made up of vectors v1, v2, up to vn, and remember, v could be a small number or it could be a much bigger number. A set S that's made up of these vectors, where each vector comes from Rn, that these numbers match, right? There are n vectors in this set, and we're in n space. A set S of vectors like this is linearly independent if the following criteria can be met. The linear combination, any linear combination of those n vectors equals the 0 vector, has only the trivial solution. And the trivial solution means that A1 and A2 are equal, and A2 and A3 are equal, and they're all equal to 0. That's the number 0 this time, not a vector, right? That's the numeral 0, the real number 0. If A1 and A2 and A3 and A4 all the way up to AN are all equal to each other and they all equal 0, then what we found on the previous screen is not true. And what we found on the previous screen is what makes vectors linearly dependent, right? So we found values of A1 and A2 in that case that were not necessarily 0, or we could. And so what we had there was linear dependence. Here we have linear independence. And so I'd like to do now an example, do this example in R3 of three vectors that are linearly independent. So my vectors are v1, v2, and v3. And a linear combination of these would be a1 times v1 plus a2 times v2 plus a3 times v3. But remember, I said on the previous screen that we can set this matrix up without writing that out necessarily. I'm going to take the first column, 1, 5, 2, and then the second column, 1, -15, and 6, and the third column, -2, -1, and 0, and use that to create an augmented matrix with the vector made up of all zeros. Then I'm going to use this matrix, row reduce this matrix to reduced echelon form, if possible, and the matrix that it results in will tell me whether or not these three vectors are linearly independent or linearly dependent. So I'll go do that now on my calculator, and I'll come back when I have a row reduced matrix. All right, there's all the work done for you. I stuck this matrix into my calculator. Of course, I could have done it by hand. This pivot's already a 1, so I'll leave that there. Multiply this row by 5 and add it to this one. That's going to give me a 0 here, and so on, right? Elementary row operations. I can do this by hand. It's not necessarily, strictly speaking, necessary at this point, but we know how to do it. But when I do, it turns it into this matrix. And remember that the interpretation of this matrix is that A1, since that's what this is the coefficient matrix for the weights, right? For the constant values, A1, A2, and so on. So this tells me that A1 equals 0, A2 equals 0, and A3 equals 0. And that gives us that this equation here, the left-hand side equals 0, has the trivial solution where A1 and A2 and A3 and so on are all equal to 0. A1 is 0, A2 is 0, A3 is 0. So all three of my weights are 0, and that means that this equation equals 0 only has the trivial solution. And in turn, that means that this collection of vectors, this set of vectors, the vectors in this set, I should say, are linearly independent. Had we found when we did this process here anything other than all three of these being 0, two of them can be 0 and one of them is something else, anything other than the all 0 solution, then the vectors in our set would be linearly dependent. But because these are all zeros, the vectors in our set are linearly independent. Okay, just one last thing on this topic. There's another way to tell if a set of vectors is linearly dependent. Actually, there are three other ways. If two of the vectors in your collection are scalar multiples of each other, then the collection of vectors is linearly dependent. Right? That's kind of how we define linear dependence in R2, and it applies here as well. If two of the vectors are scalar multiples of one another, then your set of vectors is linearly dependent. So you don't actually have to do anything here. You can see that these two vectors are, one is -2 times the other, right? So this set of vectors would be linearly dependent. Another way to tell is if the 0 vector is in your set of vectors, then your collection of vectors is linearly dependent. This is like saying there's a line in my final reduced echelon form of my matrix that's all zeros, and that just says 0 equals 0. And that means 0 equals 0. And so that also tells us that the collection of vectors is linearly dependent. And the last clue here is that there are 4 vectors in this collection, right? Not just 3. We're clearly in R3 here, but we have 4 vectors. So even if vector v4 was something like 3, 4, 5, the fact that there are 4 vectors here tells me that this collection of vectors is linearly dependent. So if 2 vectors in the set are scalars of each other, if there are more vectors than there are dimensions in the set, right? We have 3 dimensions in the space we're working on, but there's 4 vectors here. Or if the 0 vector is one of the vectors in the collection, any one of those things tells you that the set of vectors you're looking at is linearly dependent.